So now I've moved to the second textbook. The first 4 projects came from this book, more or less. I think I found some of them online. The next 3 come from this book, where you're learning technical details of how this works. At least the next 2, I think the third one might be different. Anyway, if you care, I started with this book, then I moved to this book, then I moved to this online training thing here. So there's a lot of sources with good machine learning projects. But this one, 104, is where you learn how to process input data. One big part of machine learning is you have to analyze the input data and adjust it. So I guess I'll do some of this live. We'll see how much of this is worth demonstrating. So I have old stuff here. I don't care about your stupid notifications. All right, so I'm going to throw away this old thing, move to trash, and return. So I have a clean one and new notebook. All right, there we are. So first thing they want me to do is to check and see if I have the right package version of this thing called sklearn. We're using various different machine learning libraries in these projects. So that's going to find some version number, run without errors, which is all that matters. All right. That checks to see if it's a version. It would print an error if it didn't. So now we're going to download the data. And this data is California house price data. See, something went wrong here. Okay, copy. So I add another block of code. And this is going to download a data set from some GitHub that has housing data in a zipped format, and then it's going to unzip it and give us a summary of the data. So there it is. So the data comes in, it has 10 columns, longitude and latitude of districts, they call them in California, parts of California, and then total rooms and bedrooms, population, median income, and the median house price. And what we're trying to do is to predict housing price by from these other parameters. So you can use head to see the top few records. I'll do that. Just like you would at the command line in Unix. Here's the structure of the columns. And you can see the first few records with head. And there they are, longitude, latitude, median age, total rooms, a bunch of numbers for all these things, and letters over here in proximity. That's an alphabetic field. All right. And so you can also use this thing called category of value counts. It's a very useful thing. This will give you a summary of data, more than just the head. This will give you how many there are of each value. So here it'll tell me what happened for that ocean proximity field. I could do it for any field, but this is a field with strange values. And so now I see there are 5 possible values, and here's how many of the lines in a data set have those values. You can also use describe to get a description of a database. And this will give me count, mean, standard deviation, minimum, and all that for each one of these parameters. And these are all ways to get a general idea what's in the data, which you're going to need as you plan how to make a machine language model fit. And another thing that would help would be to have histograms. So if you calculate them, you get a grid of histograms. Okay. And so this shows me how longitude is distributed. There are 2 peaks of longitude because there's the LA area and the San Francisco area. Here's latitude, again 2 peaks. Here's the age of the houses. These are Poisson-looking distributions, total rooms, total bedrooms, median house value. But now you can see what sort of distribution there are of things. You notice something funny happened to house value. There's a big spike at 500,000, suggesting something wrong with the data, like the data just hits a maximum and they don't measure value above that level or something. All right, and then we can make training and test sets. So here's some code that will make a 20% test set. So it's going to import NumPy, which is a number library, and then it's going to take 20% of it and call it the test set, and the rest and call it the train set, shuffling and splitting it. So there you go, and here's a summary of it. The training set has 16,000 lines, the test set has 4,000 lines, and here's the head of the test set, and and that's all you have, the test set. And head split this thing into various sections to make it all fit. So we see we split it up, and now we can talk about sampling, which is a big issue. There's a possible bias in your sampling. So to understand it, consider this problem. Suppose you have something that depends on whether you're female or male. And suppose females are 51.1% of the population, which is some average somebody figured out. So if you just made a random sampling of those people, then here's a histogram of what you get. The most likely thing, let me shrink it a bit so it fits on the screen. All right, the most likely thing, of course, is 51%. But you have a chance of getting, say, 54%, 55%, 48%. If you do random sampling, you might have a very non-representative sample with a percentage of an important group like female that is not representative of the sample. And this is why people that do machine learning and people that do, hold on, I've lost my instructions here. There they are. All right. People who do machine learning and people that do polling, to do polls and see who's going to win the presidential contest and such, don't do it this way. They do stratified sampling. And here's how what you do is you take the important parameter that you're worried about, and you carefully choose a sample that has exactly the right number of that important parameter. So if in this case, what we're going to do is we're going to assume that median income greatly affects housing price. That would seem to make sense. Areas where people make more money probably have higher housing prices. And so this is going to create a median income, it's going to break median income into bins up here, and then it's going to give a stratified breakdown of them. So here, it's going to give me, I think, a histogram to show, here's my 5 categories of income. So you see I'll group it into those 5 groups, and now I can view the records, because what I did here, it added an extra label to the database. We called income category, and you can see it by looking at head. Now there's another field over here called income category, so we can use this, and therefore we can split the data using a stratified sample based on that new field, instead of just a random sample, which is what the previous split was. So here, it's doing a stratified training set, planning on this income category as the category. So now, if you do that, the training set has these percentages of the categories, like 35, 31, 17%, and the test set has exactly those numbers, 35, 31, 17. You can see the 176, 176, 318, 318, to 3 decimal places. My test set has exactly the same percentage as the training set. This is stratified sampling. It's random within each category, but the number in each category is chosen to be exactly the right number. So I will not introduce a bias from my random sampling. And you can examine the unstratified data sets to see what would happen if we had not done stratified sampling. That's here. This is just a random sampling. And in a random sampling, oh, something's wrong. Key error income category. That's interesting. It existed up here. Well, I wonder what I did wrong. Let me just see if I can spot it. There is an income category. The above exception was the direct cause. If you have a listable key error income category. Well, how rude. Did I skip a line of import strange set splits factoring? Training set test set. Well, I'll just keep going. I don't know what happened there. Anyway, I was hoping to see the unstratified test set, and I did see that. Okay. Anyway, we can remove that column, and then we can do some things where you visualize the data. So let me just try removing that column. I don't know what's wrong with that one set there. I may have to fix something, but you can just skip it and keep going. All right. So this will remove that column. We don't need it anymore. And now we can visualize the data. And this is another important thing. These are just ways to manipulate data. There's important skills to have if you're going to do this. We're going to plot it by latitude and longitude. So if you do this, you get a chart where there's a dot for every zone. But the problem is when the dots all pile together like this, you can't really see how many of them there are. So it would be better to use transparent dots. And that's this one. All right, using transparent dots, now you get a better idea how dense they are in the San Francisco and LA areas. And you can even add another feature like the median house value and put it in as color. So that's another useful graph to make this one, where now you get the median house value here, and there you see that the cheaper houses are over here and the more expensive houses are on the coast in the San Francisco and LA area. And that's, so these are just useful ways to present data. All right, and then you can do correlations. Correlations are going to be important. As you try to do machine learning, you want to know which of these parameters are important to the housing price. So we're going to do correlation against the median house value. And so here you get correlation coefficients. Now, a correlation of 1 means it perfectly predicts it because it's the same thing. The median house value predicts the median house value. Median income has a very strong correlation, 0.68. 1 is perfect, 68 is pretty, 0.68 is very good, as you'd expect. Median income has a very strong effect on housing value. Rooms and housing median age have an effect in like the 10% level. Then it's pretty much nothing. And then down here, latitude has a negative correlation at the 10% level, which is just as probably a statement that LA is more expensive than San Francisco, or perhaps vice versa. So we see that most of these parameters don't really matter, and we can do a scatter plot to see in more detail what's causing these, how these correlations look like, not just the correlation coefficient, but a scatter plot of all the data. That's nice, highlights here. Now, here you see a histogram. This is median house value, median income, total rooms, and housing median age. And here's those same properties across the bottom. So on the diagonal, you get just a correlation showing what values there are. And here you get the correlation of the two. So this is median income on the x-axis and median house value on the y-axis. And you can see here's, as the income goes up, the housing price goes up. So that's reasonable. These are the ones that showed some correlation, but you see it's not very impressive. This is the main predictor of the thing we're trying to predict. And you can look at just that plot alone, and this is where you really get a chance to apply human intelligence to the learning. So here is the detailed plot of the most important predictor, and you can see there's a trend here, but you can also see, as I said before, there's a whole bunch of data at 500,000 that doesn't seem to be accurate. So there's some kind of defect in the incoming input data that it doesn't seem to catch prices above that level. And there's a whole bunch of prices here at 450 and a whole bunch at 350, even at low income levels. So that again suggests something is wrong with the data. Perhaps some of the income values are wrong. Perhaps this is missing some effect of like government subsidized housing or something. It's just the kind of thing that a human will do. Humans will look at it and remove some of the data that seems to be harming the model, where the data that seems to be an error and not really representing the trend you're trying to measure. And that's why machine learning is not completely devoid of human input. This is all the human input, all these things. You choose what to do. And there's one more technique that's useful, which is attribute combinations. Even if one attribute does not correlate well with what you're trying to find, a combined attribute might. So here, we're going to calculate some new fields: rooms per house, bedrooms ratio, and people per house. Population over houses, bedrooms over total rooms over households. These are things that might affect the price more than those numbers individually. And so now we have correlations. And so you see house value is 100% correlated, median income is 68%, but rooms per house is pretty well correlated. And so you can discover that there is a field here, rooms per house is 14% correlated, is more correlated than rooms or houses. So that's the thing. You might find that a combined new field, synthetically created from the others, is a better predictor, and that's the sort of stuff that you put in with sort of experience and intuition to change your models. So that's all I wanted to show you about that one.